EanTime supports many communication objects. A mailbox can pass objects or data, up to 128 bytes per call, between threads. A message queue is a fixed size and thus fast, data transfer resource optimized for communication between nodes. A semaphore is a counter that can be used for inter-thread synchronization and for event signaling. A region is a one-unit semaphore that can be used for mutual exclusion. Beside these communication objects, shared memory also is supported. Very efficient way to share large amount of data. Synchronization for accessing the shared memory is required in most cases. In this chapter we discuss mailboxes, which are used to pass information between threads. Threads exchange information by sending messages to, and receiving messages from mailboxes. Any thread can send information to a mailbox, and any thread can receive information from a mailbox. Two types of mailboxes are available. The type of mailbox is specified when the mailbox is created. Data mailboxes are used to send or receive messages of up to 128 bytes of data. Object mailboxes are used to send or receive handles for RT objects. Object mailboxes can be used with memory handles to make available large amounts of data. A mailbox has two queues of which at least one will be empty. The kernel ensures that a message is not queued but delivered immediately when a thread is already waiting, and reversed, does not queue a thread when a message is already queued. The thread queue holds the handles of threads that are waiting to receive information from the mailbox. The thread queue can be FIFO or arranged in order of thread priority, with better priority threads toward the head of the queue. The data queue, for a data mailbox, or object queue, for an object mailbox, contains information that is waiting to be received from the mailbox. This queue is always FIFO, so messages or objects will be retrieved from the mailbox in the same order in which they were sent. An initial data or object queue is created when the mailbox is created. The initial size of the data queue for data mailboxes is fixed at 400 bytes, enough for 3 128-byte messages. The initial size of the object queue for object mailboxes can be specified. If the data or object queue overflows, the EanTime kernel automatically creates another buffer. These overflow queues are deleted when the data or objects have been received. When you set up a mailbox to pass objects, not data, you can set up a high-performance queue with a maximum size of 64 objects. This queue is a block of memory that stores objects waiting to be sent or received. It is permanently assigned to the mailbox, and the unused portion of the queue is unavailable for other uses. To get the best trade-off between memory and performance, choose a size for your high-performance queue that is large enough for normal operations, and let the overflow queue handle unusual circumstances. These bits are ignored for a data mailbox. When information is sent to a data mailbox, it is copied from the specified buffer into the mailbox data queue. If one or more threads are already waiting for a message at the mailbox, the information is copied directly into the buffer specified by the sleeping thread at the head of the thread queue. The thread that receives the data from the mailbox is notified of the number of bytes in the message by the return value, W received. The receive buffer must be at least 128 bytes in length, regardless of the number of bytes in the expected message. The DW milliseconds parameter specifies how long the receiving thread is willing to wait for a message to be delivered. These values can be specified. No _ wait, the thread is not willing to wait. If no message is available, the thread receives an E_time exception code. 1 to 655,349, the number of milliseconds the thread wants to wait. The value is rounded to the next multiple of 10 millisecond. If no message is available within that time, the thread receives an E_time exception code. Wait _forever, indicates that the thread will wait forever. An object mailbox is used to send and receive handles for RT objects. The response mailbox parameter can be used as a return address in a handshake type of transaction. This parameter can be a handle for a mailbox or a semaphore, or it can be null_root handle to indicate that no response is expected. Before a mailbox can be used, it must be created. Typically this is done by the receiving thread, so that thread must be created first. Alternatives are to create the mailbox in the initial thread or to use object directories. The response mailbox parameters for the acknowledge portion of the transaction can be null_root handle if no further response is required at this point. This is application specific and could change depending on the system design. The response mailbox parameter can be used for a variety of purposes. It need not be restricted to a response function. Since object mailboxes can be used to send objects of any type, the application may need to determine the type of the object that was sent. Each in-time object has a different type. The following types, and where relevant, subtypes, can be returned. Process_type. Thread_type. Mailbox_type, object_mailbox_subtype, data_mailbox_subtype. Semaphore_type. Region_type. Segment_type, segment_subtype, descriptor_subtype, virtual_segment_subtype. Heap_type. Alarm_type. Queue_type. RSL_type. RSL_ref_type. We have already seen the mailbox as universal communication object for data and objects. When only data needs to be exchanged in a coordinated way with focus on minimal overhead, use message queues. Message queues, similar to data mailboxes, are used to transfer data messages of different lengths between threads. Message queues are always FIFO organized. Message queues are designed to overcome some of the limitations of data mailboxes. Specifically, a message can be bigger than 128 bytes. Emphasis has been given to optimize sending messages between nodes on the same host. Messages can be sent as short messages where the data is stored directly in the queue, or as long messages which requires a handshake between sender and receiver. The boundary between short and long messages is defined by the user when the queue object is created. Short messages are stored back-to-back in the queue, the sending call returns immediately. Each message has an administrative overhead of 34 bytes. When all the space of the queue is used up, the sender will get an E_limit failure status. A message queue, unlike a data mailboxes, does not get extended below the size specified at creation time. Sending a long message will block the sending thread until a receiving thread provided a buffer long enough to hold the message or until the timeout value given for the send is reached. The use of a message queue requires at least the sender or receiver to share the same node with the queue object. When you create a message queue, you get a fixed size buffer for queuing short messages. Every short message has an overhead of 34 bytes in the buffer that needs to be considered when you specify DW queue size. The maximum size of a short message is set by DWMSG threshold. This is an arbitrary value which determines the method used to send the message. A short message is directly stored in the buffer and can be received later. Messages longer than DWMSG threshold will be delivered as long messages. The sender of a long message is blocked until the receiver provides a buffer long enough to hold this message. A value of 0 will force all messages to be sent as long messages. Choose the values to meet the requirements of your application. Typically, DWMSG threshold is the size of your normal messages. Messages longer than. Send a message of size up to DWMSG threshold with send RT data short message. Receive RT data message will return a short message if one is available. If the message received is a long message, B success is false and the thread needs to continue with system calls for long messages. Flush RT queue will discards all messages currently on the queue without receiving them. The API for sending a long message adds two parameters, a timeout value and a user-defined 32-bit value handed to the receiving thread. To receive a long data message, provide a buffer long enough to hold the size of the message as returned from the call to receive RT data message. Note that in the current implementation the queue handle HQ is not used and is not validated. However, you should supply the handle of the queue where the descriptor was received to be compatible with possible future implementations. Cancel long RT data message will cancel the receipt of a long data message. We have already seen mailboxes and message queues as communication object. When there is no data to exchange, a semaphore may be more appropriate. A semaphore is a counter that takes positive integer values called units. Threads release units to, and wait for units from the semaphore. This can be used for various purposes. To indicate that some event has occurred, this can also be done by a data mailbox or message queue, but if there is no data involved, a semaphore is more efficient. To maintain a free/busy state on some shared resource. As a cheap response object. In-time semaphores, which are very similar to Windows semaphores, offer a number of improvements. Priority-based queuing, Windows only offers FIFO queuing. Multi-unit wait and release, Windows only offers multi-unit release. Deterministic waiting times. A semaphore stores a count of abstract units. It does not store messages or objects, so it has no message queue. The semaphore is created with an initial value, which can be from 0 up to the maximum number of units that the semaphore can store. A semaphore has a thread queue, just like a mailbox. Threads can be queued FIFO or according to their priority. If the number of units specified in the release RT semaphore call would cause the semaphore to exceed the maximum specified when it was created, the thread will receive an E_limit exception code. Similarly, if the number of units requested with a wait for RT semaphore is greater than the maximum, the thread will receive an E_limit exception code. With wait for RT semaphore, if the requested number of units are available, the requesting thread will remain running and receive the units. The thread at the head of the queue must have its request fulfilled first, even if enough units are available for the request of another thread elsewhere in the queue. A semaphore can be used for mutual exclusion, e.g. when a double-linked list is maintained, every element in the list has both a forward and a backward link. Inserting a new element in the chain requires updating more than one link, and once the updating has been started, the chain is in a bad state until all updating has been completed. To avoid accesses in such a state, all users of the list agree to wait for the semaphore unit before using the list, and to release the unit again after the list access is complete. Note that in-time does not know the relation between the list and the semaphore, so if a thread accesses the list without waiting for the semaphore unit, this will not be recognized as a fault. Another use for a semaphore is event signaling. Assume one thread monitors a temperature, and another thread can decrease the heat coming out of a burner. If we define a semaphore unit as meaning temperature is too high, the measuring thread can signal this condition by releasing a unit to the semaphore. For the burner thread receiving a unit, coming out of wait for RT semaphore, this unit then indicates that the heat now should be decreased. You may need another semaphore to increase the heat. A semaphore can be used instead of a mailbox as the response parameter for a send RT handle call. Releasing and waiting for a semaphore unit is faster and takes less memory than sending or receiving mailbox messages. With a semaphore you can implement mutual exclusion, but there is a possibility of priority inversion. Regions were invented to solve that issue. A region is an in-time object that can provide exclusive access to a resource, such as a critical area of code, with priority inversion management. That is, when a thread possesses the region, its priority is optionally raised to that of the best, numerically lowest, priority thread waiting for the same region. Thread A and Thread B must obey the protocol, wait for the unit from the semaphore before using the shared resource, buffer, and release the unit after completion. With a semaphore, Thread A waited for a unit from the semaphore and got it. Thread B wakes up and preempts Thread A. Thread C wakes up and preempts thread B. Thread C then waits for a unit from the semaphore. Thread A has the unit, so thread C goes to sleep, and thread B continues to run. Thread C has a better priority than thread A and B, but is blocked because thread A has the required resource, unit from the semaphore, and thread B has the CPU. Additional problem. After returning successfully from wait for RT semaphore, the thread may be deleted. Now the application is stuck because a unit will not be sent back to the semaphore. With a priority region 1 to 3. As above. Thread C then waits for the region. Since thread A is in control of the region and thread C is a better priority thread, the in-time kernel dynamically adjusts the priority of thread A to match that of thread C. Thread C then goes to sleep to wait for the region, and thread A is scheduled ahead of thread B because it has a better priority, temporarily, than thread B. Thread A runs and eventually releases control of the region. Now the priority of thread A is restored and thread C runs because it is no longer asleep and it has the best priority. Regions require careful programming to avoid deadlocks. A thread controlling a region should not suspend itself, or it might hold the region infinitely. When threads need to control more than one region, waiting must always be done in the same order, or else a deadlock may occur. A thread that controls a region only is deleted once it gives up control of the region. A region that is controlled by a thread only is deleted once the thread gives up control of this region. This may result in unexpectedly long delays in executing the delete operations, even in deadlocks, if the application is implemented in an awkward way. A region is a special type of a semaphore with only one unit. Regions are designed to be used by critical sections of code. A thread that is in control of or waiting for a region cannot be suspended or deleted, so also the process containing this thread cannot be deleted. A thread that is in control of a region with a priority-based thread queue may have its thread priority dynamically adjusted by the in-time kernel to ensure that the thread releases the resource that is protected by the region. Regions are released in the opposite order in which control was obtained. A specific region cannot be released. The most recently obtained region is always released first. An attempt to wait for a region that the thread already controls causes an error. We have discussed the use of in-times communication objects and now reflect on shared memory, the most efficient way to access large amounts of data if the memory can be accessed from all threads involved. Shared memory, when used across the nodes of a single host, is the most efficient way to share large amounts of data. To coordinate writing and reading of data in the shared memory, the use of semaphores or regions is recommended. Allocate RT memory allocates page-aligned blocks of physical memory out of the process memory pool. The call automatically rounds up the length, in bytes, to a multiple of 4K. The allocated pages are contiguous, they start and end on 4K boundaries. To share memory with a thread in another process, a thread in the owning process must execute create RT memory handle. After this system call, the memory has a unique handle which can be used to share the memory with other processes. Delete RT memory handle does not return the physical memory to the process memory pool, it only frees up the handle. Free RT memory deletes all contiguous physical memory that is found at the address and got allocated by calling allocate RT memory. Delete RT memory handle and free RT memory do not check if the handle and / or memory still is in use by other processes. Thus only do these calls when all other processes have finished using the shared memory. A thread in another process wanting to share physical memory space with the creating thread must execute the map RT shared memory call to map the physical memory area into its virtual address space. The handle could be cataloged in the creating process object directory or shared via an object mailbox, discussed earlier in this chapter. Note that the pointer returned by map RT shared memory need not be the same as that returned by allocate RT memory, as separate processes have different virtual address spaces. Get RT size determines the size of the shared memory mapped. Use this call to check if the allocated memory you mapped is of sufficient size. Free RT memory. Free the mapped virtual memory from the callings process virtual address space. Concurrent access to a variable shared by multiple threads always needs to be synchronized, not only in multiprocessor and multi-core systems. Intel architecture processors support synchronization by atomic operations on memory. These operations are wrapped into functions supported by the compiler and work across different operating systems. The function generates a full memory barrier, or fence, to ensure that memory operations are completed in order. Parameters passed to exchange, increment and decrement functions must be aligned on a 64-bit boundary. With InTime for Windows, you can use interlock functions to synchronize access to one variable used in InTime and Windows. Mailboxes, message queues, semaphores and regions allow information and control to be exchanged between threads. A message is sent to a mailbox or message queue, not to a thread. Semaphores and regions can be used to establish a protocol for mutual exclusion. No specific data or piece of code is associated with either type of object. The operation of all exchanges is very similar. All have thread queues which are either FIFO or priority based. Specific system calls must be used with each type of exchange. System calls can be made both from InTime or Windows, then prefixed by NTX. A thread specifies a time, in milliseconds, that it is willing to wait for a message or unit. If that time expires, or the thread is not willing to wait at all, the thread will receive an E_time exception code. If the exchange is deleted while a thread is waiting, the thread is awakened with an E_exist exception code. Shared memory allows to very efficiently exchange information between threads. Exchange of data with shared memory normally is coordinated using semaphores or regions.